So I'd like to thank Cohen and Helen for the opportunity to tell you about some tools from the uncertainty quantification community. And specifically, I'm going to tell you about surrogates for dynamic computational models and hopefully tell you what natural disasters can teach us about pharmacology. All right, so surrogates for computer models have been applied to so many applications, weather, climate, high energy physics, nuclear reactors. Today I'm going to tell you about hazard analysis and forecasting and hopefully make some analogies to quantitative systems pharmacology. So a study of volcanic hazards started about 120 years ago after a disaster in the Caribbean and Martinique. And basically, there was community memory of what data looks like about how things behave. Specifically, there was an event about 50 years prior where there was some smoke from the volcano, but no real damage, no big flows. Then in 1902, there was a devastating rapid volcanular avalanche, not sort of pretty Hawaii lava, but think more Mount St. Helens, that killed about 30,000 people in Mountainique. Now it's just sort of the start of volcanic hazard analysis as a field. And there's sorts of geophysical hazards all over the place. So here's an ash cloud from, I'm not going to try to pronounce that, from Iceland in 2010. And this got sucked up into the Gulf Stream and basically shut down air traffic in Europe for a week or two, causing billions of dollars in damage. There are remobilized volcanic flows. So you can imagine a bunch of ashes down on the ground and either a big rainstorm or a melt happens. These things are called lahars. Here's one at in Colombia in 1985 that basically took out a village and killed 23,000 people. There's other kinds of disasters, of course, hurricanes in particularly in the eastern United States. Here is one from 2018, Hurricane Michael in Florida. So a hurricane is spinning up through the Gulf, and just as conservation of mass, the hurricane pushes a whole bunch of water onto land. And this sort of called storm surge is what accounts for most of the flooding damage that happens with hurricanes. Of course, there's flooding from rains and from rivers, but most of it comes from storm surge. And from Hurricane Michael, the total damage was about $25 billion. Another kind of geophysical disaster are, of course, forest fires, but forest fires have this double whammy of not only potentially burning things you're interested in, but also of causing debris flows afterwards. So you can imagine there's a forest fire. Well, you can imagine it rains in California and there's some runoff from the rain, but basically there's not normally flooding after a forest fire, it kind of acts like one of those lahars where the debris is much easier for the rain to pick up. And these kinds of fires, it maybe is counterintuitive, but can bulk to about 10 times their volume, picking up the debris from the fire, just from a sort of typical storm. And then maybe there's storms that are more intense because of global warming. And we'd like to get a sense of what these subsequent debris flows would look like and what areas they would inundate. Just the flows following the Thomas Fire. Thomas Fire was in 2017, but the flows were just after New Year's in 2018. There was something around $2 billion in damage. And here's sort of populated areas you can see and what the effects of these debris flows look like. They're really quite disastrous. So I want to get back to volcanic flows and use the island of Montserrat in the Caribbean as an analogy to sort of an ideal clinical trial. There was a volcano observatory here. There's sort of as rich of a data set as any volcanologist has ever seen, but there's still so much this data can't tell us. In particular, it can't tell us about rare events, the events that physically we could model and the data suggests are pretty probable to happen, but we don't have in our data records, right? And that's the kind of thing we'd like to use mechanistic models to help us with. So there are some big questions about uncertainty here. The where, when, how big, how destructive. So we can use everything we know, physics and data to or really, how can we use everything we know, the physics and data, to quantify the probability of future hazards? And this is basically the same question Dan was asking yesterday. How can we use know? How can we use the biological processes that we can model and know along with data to predict outcomes from QSP models, right? So the analogy is there, I think. Um, Again, thinking about hazards, can we predict rare adverse events using these mechanistic models and as best as we can fed by data? And how good then are such hazard assessments or these sort of rare event predictions, right? How can we quantify how much we trust those results coming from mechanistic models? So this is the kind of thing we'd like to produce. So this is a probabilistic hazard map at Montserrat. The columns are looking at forecast of the probability of hazard in years. These sort of topographic maps are really the probability of inundation. We can see these numbers are kind of small, but we can see these contours are a hundredth, a thousandth, a 10,000th, and just to give us a sense of what the probability of inundation is as the years increase. But from this top row to the bottom row, we're thinking about different models for sort of the directionality of the volcano. So if the flows could go any way they wanted, we'd be in the top row. If they were constrained just to go to the northwest, where there's some property perhaps that we're interested in, then we get the pictures on the bottom. And really, we'd like to be able to sort of make these maps under any model that we consider. And such models really are describing the aleatory variability, right? There's this sort of randomness in the process from Mother Nature rolling the dice. The other kind of uncertainty we were typically thinking about is epistemic uncertainties. So really uncertainties that stem from the fact that data and models are imperfect, right? We have limited data and we know there are assumptions and simplifications in models. So for these hazard analysis, our quantity of interest is going to be an exceedance probability. So what's the probability that we exceed some critical height? And really what we have here is an indicator function that some location that we're interested in got inundated. And this is slow. This is coming from a slow mechanistic model that's just computationally intensive. But then that X, well, there's some scenario that we wanted to sample described by a probability distribution for aleatory variability. And but even that distribution was uncertain, right? We could have sort of a family of distributions that would describe epistemic uncertainty in our probabilistic models. And this is this is a bit of a simplification. We could have epistemic uncertainty showing up here, but hopefully it gives us a picture that we have this quantity of interest, which is typically an integrated quantity. And these are the things we'd like to explore, the uncertainties, but often we're constrained by how slow our mechanistic model is. So the idea is to replace these expensive computation with statistical surrogates. Lenny, who's talking right after me, can dive in more to sort of extended discussions of uncertainty quantification. And if he doesn't, you can look up his recent paper with Jim Berger, which is really nice, and also talk about things I'm not assuming here. Like often the model, of course, is quite imperfect and has inaccuracies. So look for that. But here's a sort of system that we're thinking of, right? We have some mechanistic model. It takes in parameters, initial conditions, boundary conditions. But for the purposes of uncertainty quantification, we're really looking for a mapping from these initial conditions, boundary conditions, parameters to the output or some functional of the output that we're calling a quantity of interest. And so really we're looking for a mapping of our computer model from these inputs to the outputs. And typically, regardless of if this model is linear or nonlinear, we're thinking about this other kind of mapping here that takes, well, what are the scenarios and parameters that we might run the model at, and what does that mapping look like to the model output, to some function on the model output. And here's just a sort of warning that if you look up the literature, it's grown up in a lot of communities and they all use different notations. So for the rest of this discussion, we're going to say that inputs are X and outputs are Y. And why do we do uncertainty quantification? So I showed you an exceedance probability, which is an integrated quantity. Often we're thinking about integrated quantities, but maybe you just want to approximate this computer model and get a sense of what it looks like. Maybe you want to do some sort of optimization with the computer model, or maybe you want to do an inverse, right? So you have some output data you'd like to match, and what inputs get you close to that, right? These are the sorts of things we all want to do with models. And so back to this quantity of interest, and here I've written it in a more generic form, where G here was that indicator function before for exceeding a critical depth, right? So for a location being inundated. And our goal is we'd like to predict with uncertainty the simulator output at untested inputs, right? We have some sort of limited budget for running these computer models, but we'd like to be able to predict for any input. So the idea there is then to build a statistical model of the physical model, or if we translate this to QSP, to build a statistical model of the mechanistic model. And to do that, we think about treating the output from our mechanistic model as a random function. So here's a random function with short range correlations. We could have a random function with longer range correlations. And really what we want is, well, we want one particular realization of a random function that happens to look like the output from our model, right? So we're going to model these things with a Gaussian process. Although if this was the one that looked like our data, there's nothing about it that's particularly Gaussian for this thick green curve here. What's Gaussian is that if we look at any particular input, and think about going in Y here, that this is going to have a Gaussian distribution. Over here, we'd have a Gaussian distribution. So that's what we're thinking about modeling. So we'll center it around some mean, but then we have a Gaussian process, so it has some spreads. This is sort of this line flipped on its side here. So we have some spread in the outcomes Y given by the scalar variance. And what's really important here is we have some correlation structure between two input points, right? So for two different X values, how are they correlated? This is one particular choice of a correlation structure. There's really lots that we could think about. But what we think about, what we use to build these Gaussian processes are correlation matrices between all of our training points, right? So this is a sort of thing we're going to do to build a Gaussian process. But then we want to think about all random functions. We want to think about ones that are constrained to go through or near the actual model runs, the mechanistic model runs that we do. So here's just a cartoon of 8 model runs. So here are my inputs and my outputs. And I only want to consider Gaussian processes that go through those. So, and really what I'm looking for, I have now, the blue points are the only things I actually know. That's where I could run the model. But the black here now is the meeting of this Gaussian process. And at untested inputs, like 0 here, I also get a spread for not actually running the mechanistic model there, but instead just evaluating the mean of this surrogate fit to it. And how would we use that? Well, we go back to our quantity of interest before the mechanistic model here to determine if we were inundated or not. This was really the bottleneck. But now this is fast. Now this is just a function evaluation. So now I could think about sampling with the aleatoric model. And when I sample here, well, again, I only ran these 8 points, but all of these samples I want to take from P of X given theta, Well, now I can evaluate them at, say, the median of this curve, right, at this H tilde here. And that's for one scenario, but you could say, well, maybe I would actually switch to a different scenario. Maybe I have a sort of family of these distributions I want to sample from. So you might have really to do a proper uncertainty quantification, you might need millions or tens of millions of these samples, and you can't, you're restricted if your model isn't effectively free. And building these surrogates gives us an effectively free mechanistic model. But an added advantage of Gaussian processes is we can actually quantify the uncertainty for using a Gaussian process. So in addition to sampling the aleatoric and the epistemic models, we can also, instead of evaluating at the mean, evaluate at a sample of the Gaussian process to account for the uncertainty for using the Gaussian process in place of the mechanistic model. So I know this was super fast, but hopefully I've just stirred your brain a little bit to think about how you could use surrogates for QSP models. So surrogate models, the Gaussian processes we talked about here today, can be used to quantify uncertainty for very large models that cannot be run in many times, right? So for QSP, maybe these are large, highly nonlinear, stiff QSP models. Maybe they're platform systems models. So my question to you is, what challenges could you see arising where applying surrogates might be useful for QSP models? And so where might they be useful, and what problems might you imagine? And I think for us in the uncertainty quantification community, we're super interested in furthering our techniques, which often are spurred on by actual application. So some recent surrogate Gaussian process emulator advances that were driven by application are Gaussian processes that deal with really massive output, so-called parallel partial emulators, which came from some colleagues of mine thinking about these volcanic hazards. There's Gaussian processes to handle non-stationarity in our input space and the parameters, and this came up in the context of climate modeling. And then Gaussian processes to handle large input spaces. This is actually quite still an active area, I would say, really not settled. But this first paper on it really thought about bathymetry of sort of topography under the ocean, right? How could you characterize that sort of thing into to reduce the dimension? So so we're looking for interesting applications because for uncertainty quantification, the applications really drive the technology that we'd like to develop. And so please give us applications. I'm certainly interested in collaborating, but I think I speak for the community that we are interested if there are exciting problems that you could imagine coming from QSP. Okay, and with that, I will wrap up. Thanks for your attention.